In this video, I'll be demonstrating some useful switches and sensors that can detect vibrations, shocks, and even whether something has been flipped upside down or tilted on an angle. I'm going to be talking about Mercury tilt switches, ball tilt switches, tap or knock sensors, and vibration sensors. Towards the end of the video, I'll also take a brief look at this analog component, the AETH-DX vibration and knock sensor, and I'll also show how piezoelectric components like this one can be used as an impact sensor. These might sound like complicated mechanisms, but they're actually very straightforward, simple to use, cheap, and have very low power requirements, which makes them ideal for use with microcontrollers. Accelerometers are a more accurate way to detect vibrations and movement, but for many purposes you don't need that degree of accuracy, and the switches and sensors I'll be demonstrating today can be a great solution. In this video, I'll break down how they work, what makes each of these switch and sensor components different, and how you can use them with something like an Arduino. And so with all that said, let's get started. I'll start with this one, a Mercury tilt switch. It relies on gravity to move a small amount of mercury, which either completes or breaks the circuit when the switch is tilted in one direction or the other. As you can see here, when I tilt the switch, the mercury moves within the glass bulb and either connects the circuit by touching these two metal contacts at the base of the bulb, or breaks the circuit by moving to the opposite end of the bulb. The switch would then send a corresponding high or low signal at its output pin depending on the voltage reading, which is the result of the contacts either being bridged or broken. Mercury is toxic and best avoided, but an excellent electrical conductor, and these switches typically have a very good life expectancy. Just don't use them for scenarios where the bulb is likely to get broken or damaged. These little modules are designed for easy use with microcontrollers such as the Arduino, and the pin marked S is the output signal pin. The pin marked minus should be connected to ground, and the center middle pin should be connected to 5 volts. Depending on the design of your module and the manufacturer, you might find, in addition to the main switch component, other things like resistors, transistors, or even a comparator, and those are usually there to smooth out the signal before it gets sent back to the microcontroller. These switches can be used for monitoring the tilt angle of vehicles, and they're commonly found in all sorts of electronics projects, toys, alarms, and other devices that need to be able to respond in a certain way to tilting or tipping. Now, if we look at this one, the ball switch, this is actually a variation of the tilt switch and operates in a similar way. It has a conductive ball inside, usually made of steel, so a ball bearing basically, which you can see here where I've removed the top of the component. It relies on gravity to roll the ball back and forth inside that small metal enclosure, and we can use its position to detect specific angles and orientations. For example, if something's been flipped upside down. That ball usually sits within a small confined track or cage, an enclosure. Depending on the design, it might only trigger at specific angles, and sometimes they might even have multiple contacts to indicate different positions. Just like with the Mercury switch, when the module tilts beyond a certain angle, the ball rolls towards or away from the contacts inside, and when it touches those contacts, it bridges them, closing the circuit, allowing current to flow, which then sends a signal back to the microcontroller. One thing to note with these switches is that the ball can bounce slightly when it hits the contacts, which can cause some fluctuations in the signal, and that can usually be reduced with something called debouncing, either in your code or sometimes with additional components to smooth out the signal. Now let's take a look at a tap, knock, or shock sensor. They go by different names, but as these names suggest, this one is capable of detecting an impact and is designed to be sensitive to sudden jolts, drops, or knocks. They often use a spring, like you can see here, and when something knocks the sensor, the spring flexes, either breaking or closing the circuit. Unlike a tilt switch that responds to a more gradual change in orientation, a shock sensor reacts to a more abrupt force. These are widely used in different kinds of alarm systems, for example detecting break-ins or collisions, and even for things like equipment monitoring and anti-theft systems, such as for detecting tampering. Just like tilt switches, the signal from a shock sensor may need filtering to avoid multiple triggers from a single impact. And then we'll move to the vibration sensor, similar to the shock sensor, but these are designed to detect continuous vibrations rather than single impacts, such as detecting a running engine or an electric motor, and depending on its sensitivity, even something like detecting footsteps might be possible. Inside this black tube, you can see here a metal spring which is attached to ground, and this is wrapped around a metal rod in the center that is connected to a positive voltage. A vibration causes the spring to flex and wiggle, which produces an electrical contact with the rod in the center and allows current to flow between the rod and the spring. As I tap the component here, note the vibrations causing the spring to wiggle, which ultimately results in closing the circuit and sending the signal that we need. The signal output is often just on-off or high-low, but sometimes these can be analog components and are capable of producing a varying voltage output, which allows you to make more specific measurements. Now, let me demonstrate a few simple ways that you can get started with each of these by pairing them with an Arduino. We'll start with the Mercury Tilt Switch. The circuit itself is pretty straightforward. I'm using an Arduino powered by a 9-volt battery in this case. I'm using a green jumper wire to connect the signal pin on the Mercury switch, which is marked S, to the terminal input number 9 on the board. The center positive pin on the switch is connected to 5 volts on the board with a red jumper wire. The ground pin marked with the minus is connected to ground on the board with a black jumper wire. On the breadboard, I've placed a red LED and a green LED, and each of these have a 220 ohm resistor connected just to limit the current going to the LED. The cathodes on each LED are connected to a common ground on the breadboard, which is then connected to ground on the main Arduino. And again, I've used a black jumper wire to do that. The anode of each LED is connected to an output pin on the Arduino with a jumper wire. The green LED I've connected to number 10 and the red LED to number 11. What we essentially want from this circuit is for the switch to determine its tilt position, and once the Arduino receives a signal, to indicate the tilt angle by lighting a corresponding LED on the breadboard. Now let's look at the code needed using the Arduino software. First, we declare variables for the pins. One variable we're calling sensor pin, and we have that set to pin 9. A second variable we're naming forward LED, and this is set to pin 11. The third variable we're naming backward LED, and this is set to pin 10. In the setup section, we need to set the pin mode for each pin variable. The sensor pin is an input, of course, because we're getting the input from the Mercury switch. The forward LED and the backward LED are both outputs. In the loop section, we read from the sensor pin and store that reading in a local variable called read. Then we use if statements to control what happens when the sensor pin goes high and low. Our Mercury tilt switch should output a high signal when it's tilted forward and a low signal when it's tilted backwards. The first if statement basically states that if it reads high, then to digital write the forward LED pin high and digital write the backward LED pin low. This should turn the red LED on when the sensor is tilted forward. For our second if statement, we essentially say that if it reads low, then digital write the backward LED high and digital write the forward LED low. This should turn on the green LED when the sensor is tilted backwards. Once you've constructed the circuit and uploaded the sketch, you should see that the red LED turns on when the switch is tilted forwards, and the green LED will come on when it's tilted backwards. Now, we can actually test the metal ball tilt switch with the same circuit and some similar code. First, we'll connect the ball tilt switch to the correct jumper wires. Green again going to the signal pin marked S, the positive red wire to the center pin, and the black jumper wire to the ground pin marked minus. Metal ball tilt switches often output a low signal when tilted forwards and a high signal when tilted backwards, which is the opposite of the Mercury tilt switch I was just demonstrating. And so, although the code is almost identical to what we were able to use with the Mercury switch, we'll need to make a couple of amendments. Instead of writing the forward LED pin high when the sensor pin is high, we need to now write forward LED pin high when the sensor pin is low. Also, instead of having the backward LED pin high when the sensor pin is low, we need to change the backward LED pin high when the sensor pin is high. After connecting the correct tilt sensor and uploading the updated sketch, you should see that when we tilt the sensor forward, it lights up the red LED, and when we tilt it backwards, it lights up the green LED. You may also notice that this switch is a little less responsive than the Mercury switch and needs a greater angle to get the ball to roll. This isn't necessarily a bad thing depending on what it's needed for. If you want the switch to trigger at a greater tilt angle, this could actually be a better option. Let's use the Arduino to interface with the shock and vibration sensors, and to do that we'll be using a slightly simpler circuit. We want a circuit that detects a vibration or an impact, and after receiving that signal it's going to alert us by lighting an LED. Again, pay attention to your pin connections, with black to the ground pin marked minus, red wire to the center positive pin, and a green signal wire to the pin marked S. Let's leave the signal wire connected to number 9 on the board, and we'll use another jumper wire from 10 as our output to the LED. On the breadboard, we'll connect that output wire from 10 to the cathode of the LED, and again we'll use a limiting resistor for the current going to the LED. The LED then needs to be connected back to ground on the Arduino, which we can achieve with just a single jumper wire this time. These sensors output a high signal at rest and a low signal when detecting a shock or vibration, and we need a sketch that will turn the LED on when the sensor is activated. Again, we declare two pin variables. The sensor pin variable will store the high or low value detected by the signal pin. Since the signal pin is connected to pin 9 on the Arduino, sensor pin should equal 9 in our code. The LED pin variable will store the high or low value used to turn the LED on or off. The LED is connected to Arduino pin 10, so LED pin is set to 10. In the setup section, we set the pin modes for the pin variables. Just like last time, the sensor pin variable is an input and the LED pin is an output. In the loop section, we declare a local integer variable called read and set it equal to the digital read of the sensor pin. This basically tells the Arduino to detect the voltage at pin 9 and store the high or low value in the read variable. Then we use an if-else statement, which basically says if read value is high, digital write the LED pin high and delay for 1000 milliseconds. This turns the LED on for 1 second when the sensor detects something. If the read value is low, the else statement becomes valid and we digital write LED pin low. This will turn the LED off when the sensor outputs a low signal as nothing's been detected. Once you've constructed the circuit and uploaded the new sketch to your Arduino, we can proceed with testing. When installing these types of sensors in your project, keep in mind that their position and orientation will impact the sensitivity. You may need to test different locations and angles through trial and error just to find a position that gives the response you need. Now, before I wrap up, let's take a quick look at a couple of other sensor components that I mentioned at the beginning of the video. This was one of them, the AETH-DX shake sensor, and as the name suggests, it can detect vibrations and shakes. It's an analog sensor though, and has a scale from 0 to 1024. If there are no vibrations detected, the value output will either be 1023 or 1024. When vibrations are detected, then the value of the sensor will be less, and the stronger the vibration, the lower the value. Similar to the previous components, if I take the top off of this, you can see inside it's making use of two small ball bearings to make and break contacts within the enclosure. And this is what allows us to make the required voltage reading that produces the analog signal. Let me just showcase this in action real quick. I'll be connecting the component and a pull-up resistor to an external breadboard, and we'll be connecting one leg of the sensor to the A0 analog input on the Arduino, and the other leg to 5 volts. I'll be using this simple sketch to read the analog value captured by the sensor output, and then using the serial monitor to print that value so we can visualize more easily what it's detecting and signaling back to the controller. Another interesting component capable of acting as a sensor, able to detect impacts and vibrations, are these piezoelectric plates. I can connect one lead to ground and the other to the analog 0 terminal on the Arduino, and we should be able to detect impacts and vibrations. These piezoelectric components are amazing things, and without getting too much into the detail of how they work, suffice to say when they're subjected to an impact or a vibration, it produces a small voltage, which is proportional to the force. That voltage spike is temporary and it's fast, and it can be used for detecting sudden impacts, like in the scenarios that we're looking at today. Again, let me demonstrate that real quickly with a simple sketch where, again, we'll tell the Arduino to read the analog value at A0, being produced by our piezoelectric component, and we'll print that value on the serial monitor. Of course, you'll need to think beyond the examples I've shown in this video for real-world applications. For example, if your project detects extreme vibrations, is an LED alert sufficient? Or do you want it to cut power to the circuit perhaps? Maybe you could use a Wi-Fi module and send an alert over your network to the operator. If your project detects that it's suddenly upside down, a blinking LED might be useless, but using that signal to initiate an engine cutoff perhaps, or triggering a process that can self-correct its position, would be an application for that sensor. I think this might well be one of my longest videos I've uploaded, and so if you've made it to this point, thanks very much for watching and for your support. I hope you subscribe to the channel and we'll come back for more content like this soon. But that's it for this one. Bye for now.